The reality of imaginary numbers. Mathematicians throughout the 16th and 17th centuries had been perpetually defeated by quadratic, cubic, and quartic functions whose solutions comprised of the square root of a negative number. Most of the greater minds at the time attempted, yet failed to faithfully solve these perplexing equations, many avoiding such challenges outright by the overwhelming conclusion that no single non-zero number, when multiplied by itself, could ever possibly output a negative value. If an algebraic function is graphed and will never intercept the x-axis, therefore containing no real roots, is the function solvable by the manner of mathematical definition? Italian mathematician Raphael Bombelli held a rather unpopular answer to the issue. Regarded today as the inventor of complex numbers, Bombelli, authoring the book entitled Algebra, published in 1572, was the first mathematician to incorporate square roots of negative numbers as a separate term, instead of treating them as regular radicals, further detailing complex arithmetic where real parts deal with real parts and imaginary parts with imaginary parts. In 1777, Leonhard Euler reserved the symbol I to substitute for the square root of negative 1. The same symbol I is still used extensively by first-learning students and all through advanced professors in various mathematical subjects and real-world applications. Far beyond the boundaries of the course, Algebra 2 reaches the fundamental concepts of imaginary numbers in the great plane of mathematics. Thus, complex numbers withhold an essential philosophy, an expansive importance applied to graphical and functional representation in the areas further physics, engineering, and calculatory analysis. Quantum physicists operate in a world where nothing is known completely precisely. A quantum particle's location isn't known exactly. Rather, its location is suggested in terms of probabilities. These calculations are incredibly complex and take place on a three-dimensional plane rather than a scalar plane. Complex numbers are necessary to make these calculations possible. The central role-playing concepts of phase and probability amplitude in quantum mechanics are formulated with complex numbers, following naturally as a generalization of the whole concept of probability. For example, the fundamental equation in quantum physics, the Schrödinger equation, has an imaginary number in it, and the solutions to the equation are inherently complex numbers. Imaginary numbers are also incorporated into Euler's formula. Euler's formula is essential in the subject of Fourier analysis, which finds major applications in the study of heat flow, signal processing, music filtering, data compression, image processing, as well as many other areas in the field. Complex numbers are also quite practical for modeling periodic motions, waves of water or light, in addition to fluid dynamics problems including viscosity and turbulence, giving insight into real-world events, for example, pumping oil in oil rigs, how earthquakes shake buildings, and how electronic devices, the ever so smaller transistors and microchips, would work at the quantum level. The following is a quote taken from a Q&A reported by The Guardian. Ask any physical scientist or engineer, mechanical, civil, or electrical, how they would get on without using the square root of -1. They will tell you most of our technology depends on it. For example, without using imaginary numbers to calculate various circuit theories, you would not be reading this on a computer. It is rather safe to say that complex numbers have, in some form or another, spearheaded the critical advancement of today's modern technologies we all take for granted. And for a further note, in electrical engineering, the symbol of the imaginary number I is instead denoted by the symbol J, given that I already denotes electrical current. Using imaginary currents and real numbers helps those working with alternating current electricity do the calculations and avoid electrocution. Imaginary numbers can also be applied to signal processing, which is useful in cellular technology and wireless technologies, as well as radar and even in biology, as brainwaves. Architects and structural engineers also use complex numbers in analyzing stresses and strains on supporting beams and in studying resonance phenomena interchangeable within structures as variable as tall buildings and suspension bridges. When differential equations begin to manifest in the hundreds of engineering subjects in the real world, imaginary numbers and a fundamental apprehension of calculus are best to be acquired at that point. A further mathematical application into imaginary numbers brings about the study of complex analysis, specifically the study of complex numbers together with its derivatives, manipulation, and other properties. Complex analysis is an extremely powerful tool with an unexpectedly large number of practical applications to the solution of physical problems. For example, contour integration provides a method of computing difficult integrals by investigating the singularities of the function in regions of the complex plane near and between the limits of integration, or Picard's great theorem, which states that an analytic function assumes every complex number, with possibly one exception, infinitely often in any neighborhood of an essential singularity. Complex numbers also appear in the theory of Taylor series, the theory of matrices, solving for prime numbers, and studying number theory. So why imaginary? Why are imaginary numbers called imaginary if they do exist in the real world and have applications in the real world? Why are they still called imaginary? They're not imaginary, they're real. Well, not really real, but they're still imaginary real? Well, with everything taken into account, and with the realization that imaginary numbers have such a strong impact in the real world outside of mathematics, maybe, just maybe, that's why they're so complex. Numbers.